Hello everyone, my name is Stephen Kumar Kundu and currently I'm a PhD student at the University of Missouri, Columbia and working as a graduate research assistant in the Dependable Cyber-Physical System Laboratory. Today I'll be presenting a paper. The title of our present paper is LiteVR, Interpretable and Lightweight Cybersickness Detection using Explainable AI. So let's get started. So here's my outline for today's presentation. So as we know that virtuality has gained immense popularity in various fields. We can see from the figure here that now VR is using nowadays in disaster management, military training, healthcare, industrial design, manufacturing, even tourism and hospitality. However, one of the problem of this VR usage is cybersickness, which is a significant obstacle for immersive VR experiences. The symptoms are basically the nausea, disorientation, vomiting, headache. So to explain the cyber sickness, there are different theories are stated. That is such as sensory conflict theory, postural instability theory, rest parameters theory. According to this theory, cyber sickness occurs when the eye sense motion, but the vestibular system does not. So we can see from the figure here that the lady actually engaged in a VR simulation, but suddenly she got cyber sickness, and even she left the session. And the most important part of this year that the US Congress has rejected the US Army request to spend $400 million to buy custom HoloLens headset from the Microsoft this year. According to the result that tested around 70 soldiers, there 80% of the soldiers stated that they feel cyber sickness. So we can see that the cyber sickness is now a major issue. So therefore, there is different work actually exists in cybersickness. And broadly, we can divide the cybersickness two categories. One is subjective and objective measurement cybersickness. Other one is machine learning and deep learning based methods. So subjective objective measurement may not give sufficient cybersickness measurement during immersion because we are collecting the before or after the cyber sickness happened. So this is not automated. So therefore, to automatically detect cyber sickness with different machine learning and deep learning based substance detection are proposed for using different objective and subjective measurement data. So the data may be heart rate, bed rate, or maybe nowadays in eye tracking and other data. And even to provide the trustworthiness, internet interpretable machine learning based methods already exist. So why do we need another cyber signal detection model with explanation? So if I just search in the Google Scholar, we can find more than 3,000 cyber signal detection model. So if you look at the figure here, we can see that most of explanation, most of the cyber signal prediction model are black box. So we can ask the question that how did the model detecting the cyber sickness? Does it make sense? Can I trust the model decision? Can I reduce the size of the model? So therefore, the first thing to understand is the reasoning behind machine learning model decision, specifically why and how the ML or DL model are specific decision. So and therefore another thing we have to look at that why some sample or incorrectly labeled as a misclassification. So that's the first step toward which affected the cybersickness prediction. And obviously to identify the most dominant feature for developing a lighter cybersickness detection, for instance, standalone VR headset as Meta Quest Pro. And if we develop an effective mitigation technique, we have to know the causing for the cybersickness. So in the broad level, there is two types of explanation exist. One is inherently interpretable, another is post-hoc explanation. So inherently interpretable is basically we are just developing a rule-based method or any linear model to explaining to feed the data and explain the cybersickness prediction. And the most popular way is to apply some explainer algorithm for the line and shape to explain the black box model like DL or black box ML model decision. So that's why in our proposed here we are proposing a LiteVR framework. So first of all, we are trained three deep learning model, black box model, namely long short-term memory, graded recurrent unit (GRU), and multilayer perceptron model. And then to explain this black box model, we are applied a post-hoc explanation method, namely SHapley Additive Explanation, known as SHAP explanation method. and to provide two global to provide the expression. One is global and local expression. So global expression explain the complete behavior of the model and help vet if the model at a high level is suitable for deployment or not. On the other hand, local explanation explain individual prediction and help vet if individual prediction are being made for my right choice or not. So we are after that we are actually what do we do with the explanation. So we can one of the way you can do that, we can reduce the feature set. As we know that black box model, a DL model take huge feature, and that's just not suitable for a standalone VR headset. So we are using the dataset here. We are using integrated sensor dataset to validate the effectiveness of our proposed DL models. The dataset contains the eye tracking, head tracking, and physiological signals from 30 participants. Actually emerged from 5 different VR simulations. You can see from the figure here. And there is a different type of data here. Integrated sensor, we have eye tracking data, we have head tracking data, we have physiological data, and there is a different subcategories. For instance, for the eye tracking, we have right and left pupil diameter, we have a gaze direction, and that here. So our result is very promising. So we can see from here where we calculate the precision, recall, and accuracy. We got 92% accuracy for the LSTM model, and repeatedly we get for 90% for the GRU and able for the 79%. Similarly, for the forecasting the cybersickness, we also get a good RMSE, MSE, and RE square value. We can see that LSTM also have achieved low MSE and RMSE. But our goal is here. Can we do the reduce the feature size or not? So you can see from the figure here, this is our global expression for LSTM and MLP models. So we can see from both of the figure for LSTM for the LSTM figure, we can see that most of the feature contributing cybersickness belongs to the eye tracking data. Either it's a right eye origin or normal left eye origin or the gaze direction. And we can see that as MLP model is performing not well. That's why we have a wrong explanation here. We can see that head Euler angle is most dominating feature and EGS most dominating feature. That is not true, as the cybersickness prediction accuracy is not good for the MLP model. We can see from the local expression here that we see that most of the feature contributing for the high cybersickness is belongs to the eye tracking data, and low cybersickness also belong to the eye tracking data. So our local expression, as MLP is not performing well, we can see the wrong feature ranking here. So you can see that, for instance, you can see from the left figure for the high cybersickness class, we have head rotation and y-axis, head Euler angle in the x-axis, and that, yeah. And similarly for the low cybersickness, you can see that head Euler angle in the x-axis, and even like heart rate also coming here for most dominating feature. So our goal is to reduce the feature space, and as a do or not. So we get very promising result. You can see from the table here. For instance, in the previous for the LSTM, the training time need it's almost 2076 seconds. But after reduce the feature space, we only get the same accuracy, only 376 seconds. And 7 for the parameter, you can see the LSTM, it's before it says more than 1 lakh parameter, but after reduction the feature space, we just get 19,000 trainable parameter. Can we achieve the same accuracy? Yes. You can see that even you can see the just taking 18 feature, we get higher accuracy, like 94% even that, and we actually maintain for the, and most surprisingly here is you can see that the MLP actually increased the accuracy 79 to 89%. That's mean and similarly for the regression, we get a lower RMSE, MMC that. So we can our proposed lightweight cybersickness detection method out from the other ML and DL based method for both cybersickness classification and detection, and global extension of feature space and model cell detection significantly improve the training time and inference time while maintaining the detection accuracy. And in future, we plan to investigate the more of a stereo image and stereoscopic video data to do the cybersickness with explainability. So here's the difference, and you can just scan this QR code and see our lab. Yeah. Thank you. And for a question.